Thank you, Martin, for the introduction. So, hello, everyone. My name is Max, and I'm very happy to present to you our joint work with Eleni Batziou and Martin Bichler on core stability in assignment markets with financially constrained buyers, where we consider assignment markets with bidders facing hard budget constraints. So, the deep underlying question of our project really was, so are markets efficient, and when are markets efficient, and do markets find somehow the efficient outcome by themselves? So, and I've collected very few positive results on that. So, for example, you probably all know the result by Arrow and DeBrew saying that under convex preferences, markets tend towards competitive equilibria, and those are Pareto efficient. So, the other two things I've collected here are conditions on the existence of equilibria when markets, so when the goods in the markets are indivisible, and yes, they give conditions on the existence and some algorithms how to find those equilibria in these settings. So there are quite a few positive results in that regard. However, many of them require the utilities of the bidders to be quasi-linear. So in the results I just mentioned, the latter two results are on bidders with quasi-linear utilities. And of course, this is a very reasonable assumption in a lot of applications, but there are also a lot of applications where this assumption is not really feasible. So in particular, when bidders face hard budget constraints. Of course, there's quite a lot of literature on markets with budget constraints as well. However, many of them have a quite negative flavor. So for example, there's this result by Dobzhinsky saying basically that there is no good multi-unit auction when there are budget constraints that always produces a Pareto-efficient outcome. And on the computational side, there's, for example, the result by Bichler and Walter, who considered combinatorial exchanges and allowed for arbitrary evaluations. And so their result was that computing a welfare maximizing core outcome with budget constraints is sigma to p hard. So it's indeed much harder than NP. So our idea was, so given these quite negative results on quite general markets, do we get better results if we drastically restrict the kinds of preferences the bidders are allowed to have? So the market model we consider is assignment markets, so probably one of the most basic market models where bidders have budget constraints. So the market setting is very basic, so we have some fixed number of buyers, which are depicted on the left, and we have some fixed number of items, which in this case are a banana and an apple, and each item is sold by a different seller, and bidders have values for these items, which are depicted by the numbers above or below the edges connecting the bidders with the items. Yeah, so this is just the standard assignment markets, and now we add budgets to the bidders. So for example, the bidder on the top has a budget of only one, so she can pay at most $1 for the good she demands. Just to be very clear on the setting, because there are slight variations in literature, so we assume that buyers may only receive items with prices less or equal than budgets, and we assume that as long as the prices for the items are below or at the budgets of the bidders, the utilities of these items for the bidders are quasi-linear. So, and our central goal is to find a core stable and welfare maximizing outcome in these markets. So why exactly those two properties? Well, first of all, core stability is quite surely the most standard notion of stability in game theory. And welfare maximizing, well, if we have more than one core stable outcome, we want to pick, in some sense, the best core outcome in some utilitarian sense. Yeah, so as I said, our goal was to to compute some outcomes which are core stable and maximize welfare among all core stable outcomes in these assignment markets with budget constraints. And our main contributions are as follows. First, we provide a simple ascending auction, and we prove that this auction always finds a core stable outcome. And under additional assumptions, the auction even maximizes welfare among all the core outcomes. Second, we also have, unfortunately, some hardness result. So if we don't have any additional assumptions on the bidder's preferences, then computing a welfare maximizing core outcome is NP complete. So yeah, and this is not so promising result for real-world applications. Yeah, some related literature. For example, there is Lan and Yang considering the same model and considering what they call equilibrium under allotment. And there are other works prioritizing, for example, the property of envy freeness or bidder optimality. OK, so let's jump to our simple ascending auction. Instead of giving you a formal description of the auction, I think it's better to just show you one or two simple examples because, I mean, it's not too complicated what's going on, and I think you get a better impression of what happens if I just show you these examples. So again, we have a market with 3 buyers and 2 items, and the buyers, again, have some values for both of the items and some budgets. So as always, we start with prices of 0, 0. So both items have a price of 0. And I should say that the auctioneer does not know anything about the preferences in advance, but the auctioneer just learns about the preferences by getting their reported demand sets. So the bidder sets a price, and then the auctioneer sets a price, and then the bidders report their demand sets. So, OK, what you see on the left is the price. So the current price is 0, 0. And the next 3 columns just show the demand sets at the prices. So the top bidder only demands the banana. The bidder in the center is indifferent between the banana and the apple. And the bottom bidder only demands the apple at these prices. And what you see in the column on the very right is a set of permitted items. So what happens throughout the auction is that sometimes we have to blacklist some items from some bidders. So these bidders are then just not allowed to receive these items anymore. Yeah, and the set of permitted items, so it is initialized by just all items that are available, but the set shrinks possibly over time. OK, so let's go on with the auction. So we see at prices of 0, 0, both the apple and the banana are over-demanded, so we do what we always do, and we increase the prices for both of the items. Yeah. At prices 1, 1, nothing really changes, so we still have the same demand sets, and still the banana and the apple are over-demanded, so we just increase prices again. And now we are at prices 2, 2, and there something interesting happens. So what we see is that the demand sets of the second and third bidder did not change at all. However, the demand set of the first bidder dropped from only demanding the banana to now only demanding nothing. So, and why is this the case? Well, because the banana now costs $2, but the bidder on the top only has $1 she can spend. So she doesn't have any value for the apple, so she just demands nothing at these prices. So, and now the basic idea of the auction is so that instead of keeping the prices at 2, 2 now, we jump back to the prices we had in the step before. So we jump back to prices 1, 1. But we remove the banana from the demand set of bidder 1. So basically what we do is whenever we see some drop in the demand, which can only happen if we are tight at the budget of some bidder, then we just ban this item from the set of permitted items. So, and now at these prices 1, 1, with the restricted permitted items for bidder 1, we see that we can clear the market, so we can assign the banana to bidder 2, and we can assign the apple to bidder 3. And it's quite easy to check that this is indeed a core allocation. So the only blocking pair could consist of bidder 1 and the seller of the banana. However, bidder 1 can never pay more than $1 that the seller already receives. So this is clearly not a blocking pair, and we indeed got some core stable outcome. So what was nice in this example is that we only hit the budget of one buyer at some point. What can happen in general is that we can hit the budgets of multiple buyers at the same time. So consider, for example, this simple market where we have 2 buyers, each with the same budget of 1, and each demanding a banana. So let's start here at prices of 1, where both bidders just demand the banana. So we have to increase the prices again. And what we see now is that the demand of both bidders drops to 0. And we can just blacklist the banana from both of the bidders now, because then the item would be unsold. So what the auctioneer has to do, the auctioneer has to do an uninformed choice from which bidder the banana should be blacklisted. So, and there are 2 options here. So first is only the first bidder is allowed to receive the banana. Then we have 1 core allocation with a total welfare of m, because that's the value the bidder has for the banana. Or the other option is that that the second bidder receives the banana. Then we have a welfare of only 2, and yeah, this is only a core stable outcome. So what we see from this is that in general, the welfare the auction produces can be arbitrarily low. So there is no constant factor approximation or something that we can assure that the auction will output. So, and since the auctioneer does not observe any valuations, so in this private information setting, this problem is basically unsolvable. Yeah, let's step to our theoretical results. First of all, so we show that the auction always terminates in a core stable outcome. Second of all, so if this, what we saw on the last slide, doesn't happen throughout the auction, so if there's always just 1 bidder we can blacklist, then we can indeed show that the outcome we get is welfare maximizing. So then the auction is basically deterministic, and we show that then we also get the best possible core stable outcome in some sense. If this is not the case, we cannot say too much. So the only thing we can say that if the auctioneer is very lucky and always chooses the right bidder to blacklist, then we can get to a welfare maximizing core stable outcome again. But again, so there is no reason to believe. So there is no reason why this really should happen. A few words on incentive compatibility. So in the previous slides, we just assumed that the bidders report truthfully. And indeed, we somehow have to assume this because it's quite easy to see that there is no incentive compatible mechanism for determining core outcomes in general. So in this assignment market setting with budget constraints. How can we see this? So consider this very simple example. We have 3 equal bidders, so with the same budget and the same values for the 2 available items. And let's first assume that they both report their preferences, so their valuations and their budgets truthfully. And then since there is 1 more bidder than item, 1 bidder just does not receive anything in any core allocation. So and without loss of generality, this is the first bidder. So what could the first bidder do? The first bidder could increase. So the first bidder could report a false budget. So what happens if the first bidder reports a budget of 2 is the following. It's quite easy to see that in any core stable outcome, the first bidder now has to receive 1 of the 2 items because, yes, according to their reported budgets, there is no core allocation where this bidder does not receive anything because the seller thinks that the bidder could always pay more than the other bidders. However, what is also important is that the price of the banana is not greater than 1. So again, so the bidder can afford the banana at their real budget of 1. So and this is the case because both the apple and the banana have to be sold, and the values of all bidders are equal. So and 1 apple has to be sold to 1 bidder with a budget of 1. So and this is basically the reason why the price of the other item also has to be 1. So it's easy. So it's quite straightforward to see that there just is no incentive compatible mechanism for this problem. Let's now go briefly to the full information setting. So now we assume that the auctioneer has full information about the bidder's true valuations and budgets. So, and the question is now, so can we do more? So we saw on the last slide, so if the auctioneer just has limited information, then we cannot expect to find a core-stable welfare maximizing outcome. And yeah, the question here is, so can we efficiently compute a welfare maximizing core outcome in this setting? And unfortunately, as I already said, the answer is no. So we show in our article that finding a welfare maximizing core outcome is NP-complete. I won't go into any details of the proof here, just mention two things. So first of all, showing that the problem is in NP is quite simple, so you can just formulate a mixed integer program that solves this problem. And the NP hardness proof is quite sophisticated, so we use a not so simple reduction from the maximum independent set problem to show that indeed the problem is NP-complete. So one thing, so if you recall the auction I presented you before, is so you could think that maybe there is some simple greedy approach in choosing the right bidders to blacklist, and that you get then some simple approximation algorithm for this problem. However, so all simple greedy strategies that we tried here didn't succeed. So we weren't able to find any constant factor approximation algorithm of this problem. So at this stage, I think a very interesting open problem. So let's get to the conclusions. So open questions, as I just mentioned. So maybe the most interesting open question is if there is a constant factor approximation algorithm for this problem. A second open question is, can we extend our results to more complex settings? So we know that quite fast we get to market settings where core outcomes don't even exist. But the question is, can we find a bit more sophisticated market models where we still have some core allocations and core outcomes, and where we can design a similar auction? So yes, let's get to the conclusion. So our question was, are assignment markets with budget constraints efficient? And I would say, so in general, the answer is quite negative. So as I said, we don't have incentive compatibility in general. However, there is a simple auction that finds a core allocation in any case. But welfare maximization of the auction requires additional strong properties. And even if we know everything about the bidder's preferences and budgets, it is computationally hard to compute a welfare maximizing core allocation. Yeah, so thank you a lot, and I'm happy for any questions.
Thank you. I think there's time for one question, maybe. Does your reduction imply anything about the hardness of approximation?
So the question was if the reduction implies something about the approximation. So we thought about this, and unfortunately, no, because, yeah. Because, no.